Good afternoon. Welcome to Annamalai University Faculty of Engineering and Technology. I am Professor MURUGAPPAN, Professor, Department of Civil Engineering. So I welcome all for an introduction to fluid properties, which comes under fluid mechanics, the course fluid mechanics for second year civil engineering. So this is module 1, in which we will see the basics, the introduction of fluid properties. So if you take matter, it can exist in any one of the three states, namely solid, liquid and gaseous. So the liquid and gaseous state, is combinedly called as fluid state. For example, if you take water, it can exist in any of the three states under natural conditions. In liquid form as water, as we consume, and in solid state as ice, and in gaseous state as water vapor. So matter can exist in any of these three states, namely solid, liquid and gaseous. So water can exist in any of these three states under natural conditions itself. So in solid state as ice, in liquid state as water, and in gaseous state as water vapor. So for instance, if we take the location Chidambaram, where Annamalai University is situated, water exists in two states under natural conditions. That is as liquid water as we consume, and in the atmosphere as water vapor. The water vapor content in the atmosphere is measured in terms of the parameter humidity. Whereas it does not exist in nature in the ice form in Chidambaram, but if you refrigerate water below 4 degrees Celsius, it will become solid. I'm sorry, at 0 degrees Celsius it becomes solid. Now let us discuss briefly about the varying characteristics of the solids, liquids and gases. Now if you take basically the solids, liquids and gases have different molecular structure. So if you take any matter, it consists of a number of molecules, vast number of molecules, and these molecules are separated by empty space, and the molecules, they tend to move continuously within the matter. And these molecules, they have an attraction for each other. There is mutual attraction exhibited by the molecules. That is intermolecular attraction we call. So matter, it consists of vast number of molecules, and these molecules are separated by empty space, and the molecules, they have a tendency to move continuously within the matter, and they exhibit an attraction for each other. Now when the distance between the molecules, that is the empty space we call, when the distance between the molecules becomes very small, then there is a force of repulsion which pushes the molecules apart. Now if you take solids, the molecules are closely packed or closely spaced, that is the empty space between the adjacent molecules is very meager. Whereas in liquids, the spacing between the molecules is relatively large compared to that of solids. Whereas if you come to gases, the space between the molecules is still larger compared to the liquids. So therefore, if you take a given volume of solid, it contains a larger number of molecules. Say for example, if you take say 1 liter of solid or 1 meter cube of solid, we will put 1 meter cube of solid. Say it has some n number of molecules. Now for the same volume, that is 1 meter cube of liquids, the number of molecules will be relatively less, say it will be less than n, say n1. Again for the same volume, 1 meter cube of say gas, it contains still much less number of molecules, say n2 which is n2 which is again still less than n1. So the number of molecules in unit volume of a gas is less than the number of molecules in a unit volume of liquid, and whereas if you compare the liquid and solid, for the same volume the number of molecules in a liquid is smaller than that of solid. Now coming to the differences between solids and fluids. So let us first take the spacing between molecules, which we discussed in the previous slide briefly. So in solids the molecules are closely packed. The force of attraction is between molecules is large, and because of that there is very little movement of molecules within the mass of solid, and hence the solid possess compact and rigid form. So they have a proper shape, solids have a proper shape. So the molecules are closely packed, and hence the force of attraction between molecules is large, and the movement of molecules within the mass of solid is very little, and hence as the movement is restricted and the force of attraction between molecules is large, the solids, they have a compact and rigid form and they have a proper shape. Whereas coming to liquids, the molecules are widely spaced or widely packed compared to that of solids. Because they are widely spaced, the force of attraction between molecules is relatively less compared to that of solids, and hence the molecules can move freely within the mass of liquid. So what about the force of attraction here? Because the molecules are widely spaced and the force of attraction between molecules is relatively less compared to that of solids, and the molecules can move freely within the mass of liquid, the force of attraction is there, it is sufficient, it is just sufficient to keep the liquid together in a definite volume. So here volume is definite, but shape is not fixed. Shape is not fixed. So what about the shape of the liquid? So the liquids take the shape of the container in which it is stored. So now let us come to gases. So the molecules are very widely spaced compared to that of liquids. Hence the force of attraction between molecules is very less. The molecules enjoy greater freedom to move freely. So they enjoy greater freedom. So they move freely such that they fill the entire volume of the vessel in which it is contained. So for example, say I have a vessel whose capacity is say 1 liter. Say this 1 liter is filled with a gas, some gas. Now I am transferring the contents of the gas in 1 liter to a 2 liter container, and close it. Now what happens? Now what is the volume of the gas here? The volume of the gas in the 2 liter container is 2 liters. So 1 liter has become now 2 liters. The mass remains the same. There is no change in the mass of the gas, but the volume has increased from 1 liter to 2 liters. That means the gas molecules have become widely spaced compared to that in 1 liter. So the spacing between the molecules, gas molecules, when they were in 1 liter, and the spacing between the molecules when they are in 2 liters. So here in 2 liters the spacing has increased. The spacing has increased, and therefore the force of attraction has become much less, and they enjoy greater freedom in the 2 liter container compared to the 1 liter container. So they fill the entire volume of the vessel in which it is contained. So again, summarizing the differences between solids and fluids with regard to the spacing between molecules. In solids the molecules are closely spaced, the force of attraction between molecules is large and the movement of molecules within the mass of solid is restricted, and hence the solids possess compact and rigid form. Liquids, molecules are widely spaced. The force of attraction between molecules is relatively less. Molecules can move freely within the mass of liquid, and force of attraction is sufficient to keep the liquid together in a definite volume, but the shape is not fixed. They take the shape of the container in which it is stored. So coming to gases, the molecules are widely spaced. The force of attraction between molecules is very less, and the molecules enjoy greater freedom to move freely such that they fill the entire volume of the vessel in which it is contained. So the fluids, that is liquids and gases together, they have greater mobility, that is they have more freedom to move from one place to another place, and large spacing of molecules. The spacing of molecules is wider. Now in the mechanical analysis of fluids, we have an assumption that the fluid is considered to be in continuum. So what is continuum? The matter is considered to be continuously distributed with no voids or empty space. So we have just seen that whether it is solids or liquids or gases, there are empty spaces between the molecules. In case of solids, the empty spaces is very, very less. In liquids, it is relatively large, and in gases, because the gas molecules have freedom to move within the space they occupy, the spacing becomes larger and larger when the opportunity to freely move is established. So, but here we make an assumption that the matter is considered to be continuously distributed with no voids or empty spaces. So, how can we justify this assumption that the continuum of fluids is there? Because ordinarily the fluids involved in most of the engineering problems have large number of molecules, vast number of molecules, and therefore the distance between them is small. So this allows you the freedom to assume that the continuum in fluids is justifiable. Now coming to the ability to resist external forces, the differences in solids, liquids and gases with regard to the ability to resist external forces. If you take solids, they can resist any form of external forces, say for example tensile, compressive, shear, up to a certain limit. So all solids can resist tensile, compressive and shear forces up to a certain limit. Whereas if you take fluids, whether it is a liquid or a gas, they have no, if you take a liquid, they have no or very little tensile strength. There is no ability or very little ability to resist tensile forces. So the ability to resist an external force is called the strength. Whereas the fluids can resist compressive forces only when contained in a vessel. So the fluids can resist compressive forces only when contained in a vessel. Whereas the fluids cannot resist shear stress. It undergoes deformation under the action of a shear force. So solids can resist any form of forces up to a certain limit, be it tensile or be it compressive or be it a shear. Whereas fluids have no or very little tensile strength. So later on we will talk about surface tension of a liquid. That is a very little tensile strength the liquids possess. Again, it is a surface phenomenon. Whereas the fluids can resist compressive forces only when contained in a vessel, when stored in a vessel. They cannot resist shear stress and they undergo deformation. Now when a fluid is subjected to a shear force, and as long as the shear force is applied, that is it continues to act, the fluid undergoes continuous deformation. So as long as the shear force acts, the fluid will undergo continuous deformation. This characteristic of fluid gives them the property to change shape or to flow. change shape is called to flow. So the fluid, whether it is a liquid or a gas, it cannot resist any form of shear stress. So when you apply a shear force to a fluid, be it a liquid or a gas, it undergoes deformation, and as long as the shear force continues to act, the fluid will undergo continuous deformation, and this characteristics of a fluid gives the property to change shape or to flow. Of course, fluids do offer resistance to shearing or tangential stresses between adjacent fluid layers. Say for example, if you assume the fluid to move in layers from one point to another point in parallel, say parallel layers like this, and each layer is composed of a number of molecules, and between adjacent layers there will be some resistance because of the shear stress induced, and this shear stress will actually result in opposing the movement of one layer of fluid over the other layer of fluid. The magnitude of shear stress to which a fluid is subjected to depends on the rate of deformation of the fluid element. The magnitude of shear stress to which a fluid is subjected to depends on the rate of deformation of the fluid element. When a fluid is at rest, that is in a static condition, of course there is no shear force acting on it, and no shear force can exist on it when a fluid is at complete rest, what we call static equilibrium. When we say that the fluid is in dynamic condition, that means the fluid is flowing, that means shear force is acting on the fluid element and the fluid particles are subjected to shear stresses. Now still on the differences between the gases and liquids. Now gases, it can be compressed very easily under the action of external pressure. When you remove the external pressure, what happens? The gases tend to expand indefinitely because they enjoy the freedom to expand indefinitely given the chance. So they can be compressed easily under the action of external pressure, and if external pressure is removed, the gases tend to expand freely or indefinitely, occupying the entire volume of the container or whatever it is, space in which it occupies. Whereas the liquids, they are generally incompressible under ordinary conditions, but they can be compressed under special conditions. So ordinarily the liquids can be considered as incompressible, and a liquid has a free surface. Now what is a free surface? A surface from which all pressures except atmospheric pressure is removed. A surface from which all pressure except atmospheric pressure is removed. Say for example, you consider a container in which water is stored to a depth or to a height h from the base. Now this, which is in contact with the atmosphere, so here you have atmosphere and this is water. Now this atmosphere will exert atmospheric pressure on the surface of water. Now this is called the free surface. This is called the free surface of water. So free surface exists for any liquid. So a surface, free surface is nothing but a surface of the liquid from which all pressures except atmospheric pressure is removed. Now let us define a fluid. So a fluid is a substance which is capable of flowing. So as we already discussed, a fluid cannot resist any shear stress. When it is subjected to a shear stress or a shear force, it will start undergoing continuous deformation as long as the shear stress continues to act, and therefore it changes shape or it flows. So we can define a fluid as a substance which is capable of flowing. it has no definite shape of its own. It has no definite shape, be it a liquid or a gas, it has no definite shape of its own. It takes the shape of the vessel in which it is stored. It undergoes deformation under the action of even a small magnitude of shear force, and the deformation continues to act as long as the shear force continues to act on the fluid. And the deformation continues as long as the shear force continues to act on the fluid. Now, this is an objective question you can easily answer. A fluid is a substance that you have four options. Option A is essentially incompressible, has a viscosity that always decreases with temperature, cannot remain at rest when subjected to a shearing stress, cannot be subjected to shear forces. Now, based on the discussion we had earlier, we can say that a fluid is a substance which can be easily compressed when subject to an external force. So, this option is not correct, is essentially incompressible. So, normally fluid is, we cannot say incompressible, gases are highly compressible. So, fluid means it encompasses liquid as well as a gas. So, gases are very highly compressible, whereas liquids are generally incompressible, but it can also be compressed under special circumstances. Therefore, this option is ruled out. Has a viscosity that always decreases with temperature. So, of course, we will discuss on viscosity a little later in fluid properties. If you take option D, cannot be subjected to shear forces. So, you can subject any fluid to shear force. Only thing is, when it is subject to shear force, it cannot resist the shear stress and it undergoes deformation. So, this option is also not correct. It cannot remain at rest when subjected to a shearing stress. This is correct, because they undergo deformation. So, when subjected to a shearing stress, the fluid undergoes deformation, undergoes continuous deformation as long as the shear force continues to act. So, undergoes continuous deformation as long as the shear force continues to act. Now, let us define what a liquid is. It is a fluid which has a definite volume, and the volume of a liquid varies only slightly with temperature and pressure. So, it has a definite volume. So, sorry, here a liquid, it should be liquid. A liquid has a definite volume. The volume of a liquid varies only slightly with temperature and pressure. So, the temperature and pressure has a very slight influence on the volume of liquid. So, you can take that the variation in the volume of liquid is not much, and it can be ignored with temperature and pressure, with variations in temperature and pressure. Liquids are generally considered incompressible under ordinary conditions, and any liquid, they have a free surface, as we discussed earlier, which separates it from the atmosphere which is overlying it. So, a liquid has got a definite volume, and the volume of a liquid varies only slightly with temperature and pressure. Liquids are generally incompressible under ordinary conditions, and any liquid, it has a free surface, that is which separates it from the atmosphere overlying it. Now, let us define what a gas is. So, it is a fluid which is compressible, which is highly compressible, and it has no definite volume. So, as we discussed, see, 1 liter of gas can become 2 liters or 3 liters given the freedom to expand. So, it has no definite volume. It always expands until its volume is equal to the volume of the container in which it is filled. So, if you are transferring the gas in 1 liter of in a container of 1 liter to a container of 2 liter capacity, now the volume of gas will become 2 liters. So it expands till its volume is equal to the volume of the container in which it is filled. So it undergoes significant variation in its volume and pressure even for a slight change in temperature. So even for a slight change in temperature, the variations in volume of the gas as well as pressure of the gas, they undergo significant variations. Now let us define a vapor. A vapor is nothing but a gas whose temperature and pressure are such that it is very near its liquid state. The temperature and pressure of the gas is such that it is very near its liquid state. So we term that gas as vapor. The common example is that steam. Now let us distinguish between ideal fluids and real fluids. So ideal fluids, they have zero viscosity and zero surface tension. They are incompressible. Ideal fluids do not have any resistance to flow. That is, we told that if you assume the fluid particles to move in layers, the fluid particles in one layer will offer resistance to the movement of fluid molecules in the other layer, right? So they offer shearing resistance. So in case of ideal fluids, they do not have any resistance as they flow. So in practice, in reality, there are no ideal fluids. There are no such ideal fluids. But the fluids such as air, water, which have very low viscosity, may be considered as ideal fluids. So what is the definition of ideal fluids? They have zero viscosity, zero surface tension, and they are incompressible. And ideal fluids do not have any resistance as they flow. In practice, in reality, there are no such ideal fluids, but we consider the fluids such as air and water, which have low viscosity, as ideal fluids. They can be considered or treated as ideal fluids. Whereas all fluids in nature, that is, we call real fluids or practical fluids, the fluids which actually exist in nature, they have viscosity, that is the resistance to flow, surface tension, compressibility, and they experience a certain amount of resistance when they flow. So they experience a certain amount of resistance when they flow. So let me summarize what we have seen in this introductory module of fluid properties is that, so a matter can exist in any one of the three states, namely solid, liquid or gas, and we have seen the differences between the solids, liquids and gases in terms of the spacing between the molecules, the force of attraction, then regarding their shape, and the variation in volume when subjected to variations in temperature or pressure. And also we have seen the differences between these three with regard to the ability to resist external forces. The fluids cannot resist the shear force. So when subjected to shear stress, they tend to change shape or flow from one point to another. So we can say that a fluid is the one which is capable of flowing. And before I conclude this module, fluid, we say, we will take the literal meaning, say the situation is fluid. What is the meaning of this statement? The situation is fluid. That means anything may happen. So we are not very certain about what will happen. So that kind of situation we call the situation as fluid. So fluid mechanics, please note, it is not a tough subject. Even though it is a relatively tough subject with regard to solid mechanics, so I will make the discussions very simple so that the students can understand very easily the concepts, and we will also work out a number of numerical problems as we progress further. And let me stop at this moment, and then we will continue in module 2, and we will start with the various fluid properties, starting with mass density, then specific weight, specific volume, specific gravity and all. viscosity, and so on. So thank you very much. Thank you.